Welcome to the Explainer! So, today we're diving into one of the greatest hidden mysteries of the modern world. I mean, it's something you look at literally every single day, probably for hours on end, but you've probably never stopped to wonder how it actually works. We are talking about the absolute magic of how our completely electronic screens manage to display the rich, complex beauty of human language. Let me just pose this question directly to you right off the bat. When you type a letter on your keyboard, how does your computer actually know what it means? Think about the core conflict here. Computers are entirely electronic machines. They don't have brains, right? They don't understand English or Urdu or Spanish. At their absolute core, digital circuits only possess two physical states. They're either switched on or they're switched off. And that's it. So how in the world do we get from a physical key press to a perfectly formatted text message on your screen? Okay, let's dive into this. That cascading wall of ones and zeros you might picture when you think of hacking or the Matrix, well, that's the true language of computers, binary. Because a computer's circuits can only be on or off, we represent those states with numbers. A 1 represents on and a 0 represents off. That means absolutely everything your computer does, every number it calculates, every image it renders, every sound it plays, and yeah, every single text message you send, it all has to be reduced to this binary code at its lowest level. But you can't just throw a bunch of ones and zeros at a screen and expect it to magically form the letter A. You really need a translator. And that brings us to the solution, a text encoding scheme. You can kind of think of this as the ultimate digital dictionary. It's a highly structured system that takes human characters, so alphabets, numbers, punctuation, symbols, all of it, and meticulously maps them to specific, standardized numeric codes. Then, a computer can convert those codes into its beloved binary. Without this essential system, our computers would honestly just be flashing random lights. So, now that we know what this bridge between humans and computers is called, let's look at the very first major bridge that was ever built. Enter ASCII. That's an acronym standing for the American Standard Code for Information Interchange. ASCII was the early, definitive industry standard that allowed different computers and devices to finally exchange text reliably. So how does it work? Well, ASCII takes every English alphabet, number, and basic symbol and assigns it a totally unique code number between 0 and 127. For instance, an uppercase A is exactly 65, a lowercase a is 97, an uppercase P is 80. Once the computer has that decimal number, it easily converts it into the binary ones and zeros that the hardware actually understands. To really lock this in, imagine you're typing out the word Pakistan on your keyboard. Under the hood, a step-by-step translation is happening instantly. Step 1, you hit P and the computer registers the ASCII code 80. Step 2, you hit A and it registers 97. Step 3, K becomes 107. Step 4, I becomes 105. It does this for every single letter, seamlessly translating your human word into a string of numbers, which are then instantly converted into binary electrical pulses. It's incredibly elegant when you think about it. But there is a pretty massive limitation to this early system: 128. Standard ASCII is a 7-bit system, which means mathematically it can only hold a maximum of 128 unique characters. Now, eventually they did create an extended ASCII that used 8 bits, which bumped the limit up to 256 characters, and that allowed for some extra symbols and accented letters. But still, 256 characters? In the grand scheme of human communication, that is a highly, highly limited capacity. And this brilliantly illustrates the central drama of early computing. What happens when 128, or even 256 characters, simply aren't enough for a rapidly globalizing world? I mean, ASCII was great if you were only typing in English, but what if you wanted to write an email in Urdu, or Arabic, or Japanese? What about Chinese, which has thousands of unique characters all on its own? ASCII's fatal flaw was that it completely excluded the vast majority of the world's diverse writing systems. The digital revolution was hitting a massive linguistic brick wall. The computer science community needed a massive solution, and well, they built one: Unicode. It's a breathtakingly ambitious attempt to map absolutely all graphic characters used in every single writing system in the entire world. Instead of tapping out at 128 characters, Unicode has the capacity to represent over 1 million unique symbols. 1 million. It finally opened the digital doors to the entire globe. But having a massive catalog of 1 million characters is really just step 1. How do you actually store all that data inside a computer without completely slowing it down? Unicode isn't just one size fits all. It utilizes different packaging formats, known as UTF, or Unicode Transformation Format. Think of UTF as the specific set of rules a computer uses to process and store that massive Unicode catalog efficiently. And there are three main flavors of UTF we need to understand. Now, what's really interesting about these formats is the clever engineering behind the three variants, UTF-8, UTF-16, and UTF-32. UTF-8 is the absolute champion of the internet. Why? Because it has a variable length. It can use anywhere from 1 to 4 bytes depending on how complex the character is. And crucially, it is completely backward compatible with our old friend ASCII. UTF-16 is also variable, using 2 or 4 bytes, but it is not compatible with ASCII. And finally, UTF-32 is fixed length. It forces every single character to take up exactly 4 bytes. It's mathematically simple for computer to read, but as you can guess, it gobbles up a ton of storage space. Let me explain exactly why UTF-8 is so ingeniously designed. If you want to type the English letter A, UTF-8 recognizes it's a simple character and smartly assigns it just one single byte of data. But if you want to type the Urdu letter B, UTF-8 seamlessly adapts. It dynamically expands to occupy 2 bytes of data to handle that non-ASCII character. It literally only uses the space it absolutely needs. This flexibility is exactly what makes it such an incredibly powerful and efficient tool for global connectivity. So the absolutely crucial point to understand here is backward compatibility. This is the secret to why the internet didn't just break when we transitioned to Unicode. Because UTF-8 is backward compatible with standard ASCII, it means that an old text file written 30 years ago in basic ASCII encoding works perfectly fine alongside brand new texts written today. UTF-8 reads the old ASCII code flawlessly. It preserved decades of digital history and prevented total communication chaos. Talk about a lifesaver. But what about the other formats? Consider how UTF-16 and UTF-32 handle that exact same simple English letter A. UTF-16 forces it to occupy 2 bytes, padding it with extra zeros. And UTF-32? It forces that tiny letter A to occupy a massive 4 bytes every single time. So while UTF-32's rigid, fixed length makes data processing very predictable and simple for the computer's processor, you can easily see how it eats up significantly more memory space than UTF-8 for basic text. It's a classic engineering trade-off between speed and storage. As we wrap up this explainer, remember that text encoding schemes really are the silent heroes of our digital world. We started with the conflict of how an electronic machine could possibly understand human thought. The answer was a text encoding scheme. Through incredible ingenuity, starting from a basic 128-character dictionary and evolving into a massive, dynamically expanding global standard, we figured it out. So I'll leave you with this final thought. Isn't it just amazing how a simple electronic grid of on and off signals was so carefully structured that it now successfully bridges every cultural and linguistic divide around the entire world? What new barriers will we use this technology to break next? Think about that next time you type a simple text message. Keep learning, keep wondering, and I'll catch you on the next explainer.